Okay, let's go ahead and start the class. We are going to talk about the uncertainty analysis today. And this is the first lab for lab 1, aerospace and mechanical lab 1. This is one of the few times we have a class on Wednesday. The lab material is already posted on Blackboard. The lab quiz, pre-lab quiz, the lab instructions, everything is already posted. Make sure to read the lab instructions, go through the lecture notes. The quiz is only 4 questions. I don't think it will take you more than 10 minutes to submit the answers. When you have 50 minutes, and all of the Friday to start, when you start the quiz, you have 50 minutes to submit it. There are a couple of requests that have come to me from STRC, from a couple of students who need more than, the given time on the quiz. Well, I think 15 minutes should suffice. So if you are one of those people who have registered with STRC and need more than the regular quiz time, just do this first quiz and see if you can. If you couldn't do it in 15 minutes, let me know. From the next one, I will give you more time. But I don't think you're going to need more than 10 minutes to do the quizzes. Again, the quizzes are just meant to make sure you read through the lab instructions and go to the lab knowing what the lab is about. Okay, so this is just a review of statistics today. We are going to talk about the standard deviation. We are going to talk about the data presentation, confidence interval, Z-score, student t-test, and eventually we're going to talk about uncertainty propagation. Before jumping into the statistics, we have to understand the difference between precision versus accuracy. So when you say precision, it essentially means that your measurement devices are measuring at a consistent rate, meaning that you are essentially measuring the same type of data. You don't really have any fluctuations in your measurements. Your human error is not there. If you are measuring the temperature to be 200 degrees, your next measurement is 201, 202. You don't really see that much fluctuation. It doesn't mean your measurement is accurate, though. It doesn't mean that it's close to the true value of the data. But when we talk about accuracy, we are talking about how much your measurements represent the actual true value of the data. So accuracy versus precision, and these are going to be two different sources of the error, right? The precision error and accuracy error. We can reduce the precision error by making sure that measurement environment is the same, making sure that remove the human error and fluctuations essentially. But there is not that much we can do about accuracy, because at some point you don't really know what the true value of the data is. You're trying to measure it, right? So you have a very vague understanding of how far you are from the actual true value of something you want to measure, right? This was something that we had to put out of the way before moving on and talk about statistics. So two sources of error, precision versus accuracy. But when you do the measurements, we are making many measurements, right? 10, 20, 30, and as you're going to see in the lab next week, we're going to make 30 measurements of the length of a cube. It's a very simple experiment. The goal is to help you understand the statistics, essentially. How should we represent these 30 data points together at one point? Essentially, very simple. We have to find an estimate of all of the data points combined, and then we have to calculate the uncertainty of the measurements. And we're going to see what each of these points are later on. Yes. Okay. What is the estimate? What is the estimate of our data? Let's take a look at these measurements. You have 5 measurements here, and these measurements are at different points. What we call an estimate is essentially the central tendency of your data, right? And how do we measure the central tendency of the data? In most cases, for our purpose, we usually use the arithmetic mean. Essentially, you take all the data you have, average it, right? The arithmetic mean, right? This is how you, this is the value of your estimate. So let's say you do 30 measurements, your estimate is going to be the arithmetic mean of your measurements. There are different methods of representing of the central tendency of the data, depending on the type of measurement you're making, depending on the type of the science, type of the experiment. You have to use different types of estimate or central tendency representation. For our case, it's always arithmetic mean, but the other central tendency representations are the median, which is the exact central value in a group of ordered data, and the mode, which is the most frequent value of the data. These are not very popular in engineering analysis, but one thing that can be useful in representing engineering data is geometric mean. Geometric mean is a little different from arithmetic mean in that instead of just adding all of your data and dividing it by the number of data that you have to multiply them and then take the nth root of the product of these n numbers. Okay, let's see where this can be useful. Again, in this course, I only want you to use the arithmetic mean, but I guess we need to be familiar with all of these. So let's take a look at this data. We have made how many measurements? We have made 9 measurements. One measurement has given us the value of 1. Four measurements have given us the value of 2. 3 measurements have given us the value of 9, and 1 has given us the value of 9, 0. This 9, 0 is obviously an outlier, meaning that this is the most probably a wrong measurement, right? Because it's very different from the other measurements. But if we were to use the mean to represent this data, if we were to use the mean as an estimate for this data, we would get the value of 14, right, for the mean. And 14 is higher than 9. 14 is not the best representative for these measurements, right? Because you have a huge outlier, the rest of them are all fall below 14. Outlier is very, very influential in determining your arithmetic mean. If you were to use median, 2 will be your median. And the same is true for mode. That would be 2. And again, if you use median and mode to represent your estimate, you are missing out on all of the 9s. So what should we do? We are going to use geometric mean. If you calculate the geometric mean, you fall at 4.7, which is somewhere in between 9, all of the 9s and the 2s. So in different cases, you have to use different methods to find the central tendency and an estimate for your measurements. But again, for the purposes of this course, you only have to use arithmetic mean. We don't really have these huge amount outliers in our measurement. Most probably don't. Okay, so is the estimate enough? Is the mean enough representation? And the answer is obviously no. As you can see, let's say these are a combination of 3 different data sets. 3 different data sets. For all of them, mean is exactly the same, but these are not the same data sets. So if you only use the mean to present this data, we are essentially removing all of the differences between these 3 data sets. What should we do? We essentially have to take the deviation from the mean into account. As you can see in this blue one, the deviation from the mean is not that huge, but in the purple one, the deviation is huge. So we have to have a way of including this deviation in our representation of the measurements. And how do we do that? The first thing we can do, the first thing that will come to your mind is to essentially calculate all the deviations and take a summation of all of them and use that as an uncertainty. That wouldn't be the best way to go about things, because if you have enough number of measurements and if you add all of the deviations from the mean and do a summation essentially on all the deviations from the mean, all of the deviations would be 0. Take a look at this plot. So the deviations from the mean here on all of these, if you add all of the deviations, would give you a 0, which essentially means that there is no deviation, right? You add all the deviations. So what should we do? We come up with this new parameter, which is called the standard deviation, or the root mean square deviation. I'm sure you have seen this before. The standard deviation calculates the deviation, takes it to the power 2, sums all of it, and then takes the square root. So the reason we use the standard deviation is because if we just use regular deviations, we won't be able to see how much we deviate from the mean. Okay. So using the estimate and this deviation, we should be able to show present our measurements. We are presenting the central tendency, and we are also presenting how much we deviate from the mean. Let's move on from this slide. Okay, but is the deviation, standard deviation, enough to show the uncertainty of your data? And the answer is no. We have to play with the standard deviation a little bit. We have to add some things to it to make it a good uncertainty calculation, essentially, a good measure of uncertainty of the data. What are the types of uncertainty? We have two types, as we thought. One of them refers to the precision. One of them refers to the accuracy of the data. We have systematic or bias errors that are fixed. These are, doesn't really matter how much you repeat, how many times you repeat your experiment, this error is going to be there, and there's basically nothing we can do about it, essentially. Again, if you have a thermometer here, and if you measure the temperature of the thermometer, our knowledge, our understanding of the temperature is based on the value that we see on the thermometer, not the actual value of the temperature here. So the thermometer is giving us the wrong value. Our understanding of temperature in this room is not correct, it's wrong, right? So there is nothing we can do about this accuracy errors, essentially. And then we have the random or bias errors that we can alleviate or understand based on our uncertainty analysis specifically. Okay. Okay, so estimate, we understand a little bit of uncertainty, but then we want to go a little further and calculate the uncertainty. Before doing so, we need to understand, or we need to know what does uncertainty mean. So whenever we present our data in this way, meaning an estimate plus and minus an uncertainty, what does it mean? It essentially shows us how probable it is for your measurement to fall within the interval that is going to be given to you with this uncertainty. What does this mean? Let's say my estimate is 2. Let's see if I have anything here. Yeah, like here. Let's say my estimate or mean is 2, and then my uncertainty is any value of 1, right? That uncertainty is based on the level of confidence we have in our data that we are going to discuss. That uncertainty is going to tell us how probable it is for our next measurement to fall between 1 and 3, right? Because the confidence interval is between 1 and 3. And your whole job when you're doing the measurement, when you're done with any of the measurements in this course, your whole job is to calculate these on the confidence intervals and uncertainties. Okay. The most famous example here that you have always seen is the likelihood of getting a face or getting a back of a coin when you are flipping a coin. Any questions so far? Am I going too fast? I usually go too fast in these parts because I think you probably know most of this, right? So this is just a review. But if you do have a question, just stop me. Okay, let's move on. The idea is if you increase the number of measurements, your frequency distribution is going to, let's say you do infinite number of measurements. Your frequency distribution is going to look like this. This is what we call a bell curve, a normal distribution, or Gaussian distribution. And so we have to use this bell curve to come up with a method for uncertainty analysis. And that method is called the standard normal distribution, or z-score method. So what we do is we have found, I mean not we, as statisticians, have come up with a standard normal distribution. What is a standard normal distribution? It's a normal distribution which mean is 0. See, it goes to -3 or negative infinity and positive infinity from both sides. And using this normal distribution, they have come up with a z-score table that when you multiply the z-score table or z-score values that you read off of a table by your standard deviation, you can find the uncertainty of your data. And they have the mathematical proofs and everything for this, which is definitely outside of the scope of this course. So the idea is, based on this normal distribution that was found before by statisticians and the standard deviation of your data, you can find the uncertainty of your measurements. Very simple. Okay. But how do we find the z-score for our data? The z-score is very dependent on how accurate you want to be in your representation of your data. And this is what we call a confidence level. Right? How confident you want to be in your confidence interval. You want to be 90% confident, or do you want to be 75% confident? What does 90% confidence in confidence interval mean, or in uncertainty analysis mean? It essentially means that, let's say, I tell you that find the uncertainty of this data for a 90% confidence. It essentially means that whatever interval, whatever measurement plus minus uncertainty you give me, is your next measurements are going to fall within this range with a 90% probability. Okay? Does it make sense? Okay. So if you increase the confidence level to 100%, how big your confidence interval do you think will be? So essentially, if we say I want to know with 100% confidence that my next measurement is going to fall within the range that you are giving me, how big your interval will be? Yes. It's exactly. Essentially, from negative infinity to positive infinity, right? We can't really have 100% confidence. That's the idea. Okay, so the z-score tables are usually like this. We're going to come back to this table and see what all of these numbers mean. But you don't really need to use z-score tables for this class. You can just, there are many z-score calculators online. Just give them a confidence interval, they give you a z-score value. Okay, this is not the point of the course. As long as you can give me a good confidence interval, we'll be happy with what you have done. But I guess we talked about this. Let's go through an example together to make things a little more clear. Let's do a better reminder, and then we're going to move on. In this example, we have a measurement that has a normal distribution with mean of -4 and a standard deviation of 5.2. We want to find the interval in which 90% of the population lies. Okay, so what should we do? We should take this 90% and go to the z-score tables and find the z-score value. So the idea is there is 90% probability that your next measurement will fall within this range, within this confidence interval. Okay, let's take a look at the bell curve, the standard bell curve. So we want our measurement, we want 90%, we want to have 90% confidence that our measurement will fall here. Essentially, we want to make sure that our measurements fall within 90% of the area underneath this curve. This is the frequency distribution, right? We want to make sure that the measurements fall under this bell curve, right? In this area, 0.9 of the area of this bell curve, right? So we want to cover 90% of the area from each side. Does this make sense? again, I'm sure you have gone through this, and I don't really, it's not a point to go in detail with these. There's no point in going in too deep with these analyses. Okay, so we want to cover 90% of the area. But the z-score tables that we have are half z-score table, because this is, we do have a symmetry line at the center at 0. So whenever we say 90, it essentially means that we want to cover 45% in the positive direction, 45% in the negative direction. And in our z-score table, we have to look for a 45%, right? Because these are half z-score tables, meaning that it gives you the confidence interval of half the curve. Where does 45% lie? Let's see, somewhere here. See, 45. Okay, let's take this number. From this number, how do we read the z-score value? This is going to be 1.6. This is the first part of your z-score value, and then we go top. It's going to be 1.65, right? 1.6 is going to be the first two digits, and then whatever you see up top there is going to be the third digit of your z-score. Again, what the method is, we give you a confidence interval, 90%. You divide it by half. You take that half to here, find the closest number, and of course you have to do the linear interpolation, and then read the first two digits from here, the third digit from the first row. So your z-score is going to be a positive 1.645 and a negative 1.645. Very easy. And then using this, just have to multiply 1.645 with your confidence interval, with your standard deviation. You have the mean, which essentially means that you should be able to find your confidence interval at the end, which means that x is equals to your estimate, which is your mean -4 plus minus 8.554. Or we can say that x has to lie between -12.554 and 4.554. Do you have any questions? Yes.
Where's your area measurement?
Pardon me?
Where's your area measurement?
That's the standard normal distribution, right? Just have to, I guess, read more about the standard normal distribution. The idea is the probability of something happening is essentially the area underneath this standard normal curve, right? Okay, let's move on. There is another example. We have a certain steel bar that is measured with a device which has a known precision of plus and minus 0.5 millimeters when a large number of measurements is taken. How many measurements are necessary to make sure that the mean length always is the range plus and minus 0.2 with a 95% confidence level? Okay, so we have a precision of plus minus 0.5 millimeters, which tells us the standard deviation for us has to be 0.5 millimeters. We want to know the minimum number of measurements here. Let's talk about the t-score method, and then let's move on, and we're going to come back to this later on, because you need to know a little bit about t-score method. So let's talk about cases where you don't really have enough measurements. Usually you have less than 25 measurements. Right? You're not dealing with a population, you're dealing with a very small sample. Right? The z-score method is going to become less and less accurate as you reduce the number of measurements. So how can we fix this problem? We are going to use a different method that is called the student t-distribution. The reason we call this a student t-distribution is because the guy who developed this method published the method under the name student. That's the only reason. And the reason he has to publish the method under this name is because he was under an NDA for a beer company. He couldn't really publish the method under his own name. So that's why he used a student. And the method's name has become the student T distribution. The difference between these two methods is that instead of a z-score, you have to find the t-score, right? So the distribution, normal distribution is a little different. Yeah, we don't want to go into the details with this, but eventually your uncertainty delta can be calculated using the t-score multiplied by the sample standard deviation. We don't use sigma anymore because we are talking about a small sample, but the calculation is the same thing. So S and sigma are essentially the same thing. The calculation for them is exactly the same, divided by the square root of n, which is the number of measurements you have. Okay. Again, what is the cutoff line here? The cutoff line is the 25 measurements. So how do we read a t-score table? You have to find a degree of freedom of your calculation. Degree of freedom essentially is the number of measurements you have. And then you have your confidence interval that is given on top, 50%, 90%, 80%, 90%, 95, all of those things percent as a subscript for t. Using your degree of freedom and using your confidence interval, you just read a t-score off of the table. Very simple. The only difference here is you have to know the number of measurements, and you have to include it in your calculations. Again, for the purposes of this course, you can just use an online calculator to do this. So, but the main difference between the two, other than the t-score, is in the inclusion of the square root of n. The reason we include the square root of n here is essentially it is the uncertainty of the means. I don't want to get into that discussion. I'm sure you remember it from your statistics, but the uncertainty calculation is a little different. Okay, so using this information, let's go back to this example and go through it. We are given the standard deviation as 0.5. We are also given the uncertainty as 0.2. So we want our, in this case, z, because we're dealing with the population, z divided by the square root of n multiplied by your sigma to be equals to 0.2. We are given 95% confidence. 95% confidence, your z-score is always 1.96. Again, we can go back to this table and read that. So 95% confidence, 95 divided by 2 is 47 point something, 47.5 specifically. And this is the value we have here, 47.5%, 1.906. So your z-score is 1.96. We read the z-score from the table. You have the standard deviation. You can find the minimum number of data you need, measurements you need for this confidence interval to happen, which is 25. Any questions? Okay. Let's talk about this example and then we move on to the experiment we're going to do next week. The example tells us we have 10 observations of a voltage that has been made as the average voltage is 15 volts and the sample standard deviation is plus minus 0.1 volts. We want to determine the uncertainty given at 95% confidence level. The first thing you want to do, this is a small sample of uncertainty distribution, so the first thing you want to do is to find the degree of freedom. And how do we calculate the degree of freedom? We just take the number of measurements, which is how many, we are told that there are 10 measurements, and then subtract it by 1, which essentially means that your degree of freedom is 9. At 95% confidence, for a degree of freedom of 9, 95%. This is going to be your t-score, 2.262. means that we can easily find the uncertainty. We are given the sample size deviation as 0.1. T we read as 2.262 divided by the square root of 10. Uncertainty is 0.0715 volts. And then we can find the confidence interval. Any questions so far? No. Okay. So our focus, the main focus that we have for this experiment is the propagation of uncertainty, not uncertainty calculations themselves. And I'm not sure if you have ever had a discussion about propagation of uncertainty in your statistics course, if you have taken any statistics course. But propagation of uncertainty is very important for us engineers. The reason is you don't really use, like whenever you're measuring voltage, you're not measuring voltage for the voltage itself. You're measuring voltage to calculate power, for example. So you have to measure voltage and current, and then calculate the power using those two, right? And voltage measurement, current measurement, both of them have uncertainties, right? We want to know how these two uncertainties propagate to power calculations, right? That is the goal. Should we just sum them up? Should we take the average of uncertainty? What should we do, right? And in our experiment here, we essentially want to know how much the uncertainty of measurements of length, height, and depth propagates to the volume calculations. You're given a cube. It's called the 1 by 2 by 3 cube, 1 inch by 2 inches by 3 inches, essentially. You have to make the measurements like 30 times of each side, calculate the uncertainty, and then calculate the volume, and calculate the correct uncertainty for the volume. So the uncertainty that is propagated to the volume. But how do we calculate the propagated uncertainty? There are different methods, but the method that we want to focus on is called the Klein-McClintock method, which essentially tells us the uncertainty calculation can be propagated uncertainty can be calculated using this equation. Yeah. But there are a couple of things requirements that need to be met before we can use the equation. The most important one is that the variables you're using for the propagation calculations have to be independent from each other. Meaning, like in this specific example, we have length, depth, and height, and they have to be independent from each other, which they are. Length doesn't really depend on height, right? They don't really change with each other. They don't have to. So we can use this methodology. We can use this equation. But how do we calculate how do we use the equation? Let's take a look at each part one by one. So in the first part, any W's are uncertainties. Just to make sure we understand this. The first part is the partial derivative of your function, which is r, with respect to your first variable. What is our function in volume calculation? The function r is volume is equals to depth multiplied by height multiplied by length, right? Okay. What is the first variable? Let's say the first variable is length, right? So we want to take the derivative of your volume with respect to length. What is the derivative of volume with respect to length? It's just a regular function. Let's say v is equal to x by z, and I want to take the derivative of v with respect to x. What is the result of that function? Y multiplied by z, right? It's just a mathematical thing. Very simple. And then you multiply it by the uncertainty in that for that specific variable. You do the same thing for the rest of it. You do the calculations, use the mean values for these derivatives, multiply them by the uncertainty. It will eventually give you the propagated uncertainty into volume. Let's take a look at this example problem. We have, again, this is a volume calculation example. We are given the length as 12 plus or minus 1.101, width as 5 plus minus 0.053, and height as plus 3 plus minus 0.01, 0.125. Volume is essentially all of these multiplied by each other plus the uncertainty. We don't know how to calculate the uncertainty. We have to use this method. I don't think we have. Let's actually solve this right here. Okay, so what was the equation? W of the propagated uncertainty is partial volume, partial x, multiplied by the uncertainty of x. Let's call it W of x, plus partial volume, partial y, uncertainty of y, partial volume, partial z. I'm sorry, partial volume. We don't have x, y, and z. We have L and, let me just, L, partial volume, partial W, uncertainty of W, partial volume, partial H, uncertainty of H. So this is width multiplied by height, multiplied by this uncertainty, which is 0.101, plus this, which is length multiplied by height, multiplied by this uncertainty, 0.053, plus, and all of these are to the power 2's. So this is to the power 2, this is to the power 2, and then we have to take a square root. And we have length multiplied by W multiplied by 0.125. And for these, we have to use these average values. So 5 multiplied by 3, length is 12 multiplied by 3, and 12 multiplied by 5. Take all of these to the power 2, and take the square root eventually to find the uncertainty of the volume calculation. Essentially, uncertainty that is propagated to the volume. Do you have any questions? Okay. So again, you have to go to the lab on whenever lab session is, and the lab is going to is located in the basement of T100 main building. Room number is A021A, and just you'll be given a cube and a caliper. If you don't know how to use a caliper, your TA is going to explain this to you. How to use a caliper. We're going to have two to three groups in each section. All of the section together has to do early measurements of each side. And then I will give you on the lab instruction, you are given different confidence intervals. For those different confidence intervals, you have to calculate the uncertainty, you have to calculate the propagated uncertainty, and go from there. There will be one question that is going to ask you to use the student T method to do all of these calculations. For the student T method calculation, just take the first 25 measurements. Don't use the alternative because the student T method that we have only has up to 25 degrees of freedom, essentially. Yes.
So just to clarify, the equation that we just worked through, that's to solve for the final uncertainty of the final value.
Yes, that's
Okay.
2 question marks. Okay, if there's no questions, don't forget about your quiz on Friday, and I'll see you all on Monday.